are actually the step function. They're all just approximations. And it's true, any finite sum of sine waves will never be perfectly flat, except for a constant function, nor will it be discontinuous. But Fourier thought more broadly, considering infinite sums. In the case of our step function, it turns out to be equal to this infinite sum, where the coefficients are 1, negative 1/3, plus 1/5, minus 1/7, and so on for all the odd frequencies, and all of it is rescaled by 4 divided by pi. I'll explain where those numbers come from in a moment. Before that, it's worth being clear about what we mean by a phrase like infinite sum, which runs the risk of being a little bit vague. Consider the simpler context of numbers, where you could say, for example, that this infinite sum of fractions equals pi divided by 4. As you keep adding the terms one by one, at all times what you have is rational. It never actually equals the irrational pi divided by 4. But this sequence of partial sums approaches pi over 4, which is to say, the numbers you see, while never equaling pi over 4, get arbitrarily close to that value, and they stay arbitrarily close to that value. That's all a mouthful to say, so instead we abbreviate and just say the infinite sum equals pi over 4. With functions, you're doing the same thing, but with many different values in parallel. Consider a specific input, and the value of all of these scaled cosine functions for that input. If that input is less than 0.5, as you add more and more terms, the sum will approach 1. If that input is greater than 0.5, as you add more and more terms, it would approach negative 1. And at the input 0.5 itself, all of the cosines are 0, so the limit of the partial sums is also 0. And that means that, somewhat awkwardly, for this infinite sum to be strictly true, we do have to prescribe the value of this step function at the point of discontinuity to be 0, sort of halfway along the jump. Analogous to an infinite sum of rational numbers being irrational, the infinite sum of wavy continuous functions can equal, honest to goodness equal, a discontinuous flat function. Getting limits into the game allows for qualitative changes, which finite sums alone never could. There are multiple technical nuances that I'm sweeping under the rug here. Does the fact that we're forced into a certain value for the step function at the point of discontinuity make any difference for the heat flow problem? For that matter, what does it really mean to solve a PDE with a discontinuous initial condition? Can we be